So let's look at solving a problem using linear equations. So when 5 times a certain number is reduced by 4, so 5 times this number, that's x, is reduced by 4, minus 4, the result is the same as adding 7 to 4 times the number. So the result is equal to 7 plus 4 times this number, that's x. So 5x minus 4x must be equal to 7 plus 4, x is equal to 11. That number is 11. We did these in first year, okay? Or similar ones. Okay, I think of a number, it's question 7. I think of a number, it's increase it by 4 and double the answer. I think of a number, I increase it by 4 and I double that value or that answer. The result is equal to 20 more than the number, so it's that number plus 20. So 2x plus 8 is equal to s plus 20, x plus 20. 2x minus 8 is 20 minus 8, x is 12. That's the number I was thinking of. Let's look at question 15 from page 11. 166 people live in an apartment block. Of these, x are women. Okay? There are 8 fewer men than women. X minus 8 men. And there are 30 more children, so there are x plus 30 children. How many people live in the block? So how many women live in the block? So x is our variable for women. So women plus men plus children is 166. So that's equal to x plus x minus 8 plus x plus 8 is 166. So 3x is minus 8 plus 30 is 166. So 3x is equal to 166 minus 22, that's equal to 144. X must be equal to, if I divide both sides by 3, x is equal to 48. So now we're going to move on and we're going to talk about inequalities and plotting numbers on a number line, okay? So we'll be plotting numbers on the number line, and there's 3 different types of numbers we'll be plotting. There'll be the natural numbers, which are the whole positive numbers from the natural set of numbers. There'll be the integers, which are the whole positive and negative numbers from the set of integers which we note by z, and n for the natural numbers. And we'll also be working with or talking about real numbers. And basically, real numbers are all, this is real here, all the numbers, including fractions, decimals, natural numbers, integers, all the numbers. And a capital R signifies the set of real numbers. And we're also going to talk about or meet with this notion of inequalities, okay? So here's our less than or equal to sign, and we'll say 5 is less than or equal to 60. 5 less than or equal to 60. Now, x plus 3 equals 7. That's an equation. One side is equal to the other, okay? But x plus 3 greater than 7, that's an inequality. This side is not equal to this side, okay? And there's 4 different types of inequality signs. We're just going to mention all the facts here before we start working on examples, okay? But the first sign looks like this, is greater than. The second one is less than, is greater than or equal to, is less than or equal to, okay? And if we were to look at inequalities represented on a number line, let's say we have a number line that goes from 1, 2, 3, 4, 5, 6. Okay, we've just picked a piece of the number line, and we want to represent x, the inequality x, the value of x on the number line is greater than or equal to 4, and x is a whole positive number. Okay, so that's why we haven't got any minuses, minus 1, or any of that stuff going on down here. Okay, so we're all okay. So x is greater than or equal to 4. So it's greater than or equal to 4. So we'll mark 4 with a dot. 5 is greater than 4. 6 is greater than 4, and we're using dots when we talk about marking any values of x on a number line that are from the natural numbers. We'll use dots, and we'll also use dots if we're talking about x being well, we'll come on to it. If we were talking about x being an integer from x is an element of z. But anyway, we'll stay with this for now. X, let's look at this second inequality. X is greater than minus 2. Actually, that should be z for integer. Okay. X is greater than minus 2. So, yes, I have it here. X may be all integers greater than minus 2. Okay. And we're going to use dots here as well. So, we have our number line. We're going to represent this equality that x is greater than minus 2, and we're told here that x can be a negative number. So it's greater than minus 2. So if there's no equal sign or greater than, there's no equal line there, okay? So we can't put a dot here at minus 2. We start at minus 1, 0, or any numbers that are greater than minus 2, but not minus 2 itself because there's no equal sign there. Okay. Let's look at showing the inequality x is greater than or equal to 3, and x is a real is a number. X can be any real number. Okay. So if it's a real number, we're going to use a really thick line. We're not using dots. We're using a thick line. And we may use a full dot to start the line or an open dot. Let's see what we'll do here. X is greater than or equal to 3. So here's our number line here. Greater than or equal to 3. So I'll put this full black dot because it's equal to 3. And I'll do a really thick line to say that x can take any of these values along here. X is greater than or equal to 3. Now, if that said x is greater than 3, I would have started my representation with what we call an open dot, not a full dot. The full dot is if we have a greater than or equal to or less than or equal to, because we include it with the full dot. The open dot is greater than or less than. We'll learn more by example. Okay, so let's talk about combined inequalities. And really we're just saying that, if if 8 is greater than 3, then, it's fair to say, and it's the same thing to say really, that 3 is less than 8. So basically we've brought the 8 this side and the 3 that side. So the 8's over here now and the 3 is here. But note how we've switched the direction of the sign. If x is greater than or equal to 5, then 5 is less than or equal to x. Okay, so we've switched our position of x in terms of being here or here, but we've also flicked the sign, and it's the same thing. So we can interchange the position either side of an inequality, but we must be careful to flick the sign. Okay. What about x is greater than or equal to 2, and x is a real number, and x is also less than 5. So x is this value that's greater than or equal to 2, but it's also less than 5. Anyway, right up close tight to 5, because it can be a decimal, remember, it could be 4.99999, but not actually 5, because it doesn't say equal to. So we can recombine this inequality by saying, okay, x is greater than or equal to 2. Well, the other way of writing that, which we've learned up here, is to just switch these around so that 2 is less than or equal to x. Okay? And we're looking now to combine that with our x is less than 5. So we've x greater or equal to 2, but x also less than 5. So we kind of have x in the middle here where it's greater than or equal to 2, but it's less than 5. So if we have 2, 3, 4, 5, 6 on the number line, and it's a real number, so we use a thick line, but we're saying that this value of x is greater than or equal to 2, so it could be equal to 2, but it's greater than or equal to 2, but it's less than 5. So it doesn't include 5, so we'll have the open dot on 5, and we'll just, because they're real numbers, we'll have a really thick line connecting the two on our number line. So this number line represents the fact that x can float anywhere between here and there. Okay? Now, some examples. If x is less than 3, its values are what? Okay, and it's also a natural number. Well, if x is less than 3, it's a whole positive number. Its only values can be 1 and 2. Can't be 3 because less than 3. It's a natural number, so it can't be minus 1, 0. It can only have two values, 1 and 2. Okay. What about if we graph the inequality x is greater than or equal to minus 3 and x is an integer? Okay, so we draw our number line. Okay, and we mark 0, 1, 2, minus 1, minus 2, minus 3, minus 4. Where it's natural numbers, so we're going to use dots, not a really thick line. And x is greater than or equal to 3. Okay, so minus 3, sorry. So it's greater than or equal to minus 3. There's a dot there. Greater than, greater than, greater than, greater than. And we could keep going on forever and ever and ever and ever. Okay, that's the inequality. X is greater than or equal to minus 3, where x is an integer. For this one, x and integer, so we're using dots as well. Apologies, that's a different question. My mistake, sorry. But this is an integer, so it's dots as well, not a really thick line. Natural numbers or integers, inequalities, we describe them on the number line with dots. Let's graph the inequality x is less than or equal to 4, and x is a real number. It's going to be a really thick line. Okay, x is less than or equal to 4. So we do 5, 4, 3, 2, 1, 0, minus 1. And it's less than or equal to, so we'll start with a really thick dot, full dot, sorry, and a thick line showing that all the values for which this inequality will hold true. Okay. What about if we graph x is greater than 3, natural number, so that means we'll use dots, draw a number line, 1, 2, 3, 4, 5, 6. It's greater than 3, so it has to start at 4, the next whole number up, because it's a natural number, not a real number. Okay. What values can x have if x is greater than or equal to 3, less than or equal to 6, and it's from the set of natural numbers, so it's a positive whole number? Well, less than or equal to 3 can be 4, can be 5, less than or equal to can be 6 as well. Okay, m is a multiple of 4. Find all values of m so that m is greater than or equal to 10, less than or equal to 24. Okay, so m is somewhere between 10 and 24, but it has to be, the values of m have to be a multiple of 4. So the first one up from 10 is 12, 16, 20, less than or equal to 24. They are the values of m which satisfy this inequality. So let's kind of work with inequalities now like their equations, in that we'll try and solve the inequalities, okay? And there's a little rule we have to be very aware of, that if an inequality is multiplied or divided by the same negative number on both sides of the inequality sign itself must be reversed, okay? Must be reversed, R-E-V-E-R-S-E-D, okay? Really, really important. And if you can, when you're solving inequalities, it makes sense in a minute, try and keep your x value to the left, and the inequality sign at the end will point in the direction of where you're marking on the number line. So, solve the inequality. 5x minus 3 is greater than or equal to 12, and the values of x we're talking about are whole positive numbers, okay? And graph on the number line. So, we simply say 5x minus 3 is greater or equal to 12. 5x is greater or equal to 12 plus 3. 5x greater or equal to 15. X is greater or equal to 15 over 5. X is greater or equal to 3. draw your number line, 1, 2, 3, 4, 5. It's natural numbers, we're going to use dots, and we just mark 2 or 3 places on the number line. Second example, solve 4 minus 3x is greater than minus 5. We're talking about integers, we're going to use dots. These are the whole positive and negative numbers. So minus 3x is equal to minus 5 minus 4. Minus 3x is greater than minus 9. I should have said greater than as well. So now let's divide both sides by minus 3. Okay, because we want x to be positive at the end. We want our value on this side to be positive. X is greater than or equal to whatever it is, doesn't matter, but it has to be positive. So to make it positive, we'll divide both sides by minus 3, but our rule over here says that if we multiply or divide the terms either side of the inequality by a negative number, then we must flick the sign. Okay, so minus 3 divided by minus 3 gives us x, and we flick our sign. Look at the way it was here, now look at the way it is. We flick it, and minus 9 divided by minus 3 is 3. So x is less than 3. We started this way, now we've gone that way because we divided both terms by a negative 3. Negative anything, but in this case a negative 3. So x is less than 3, so we do our number line, 0, 1, 2, 3, minus 1. We're talking about integers, so we'll show that we know we're talking about integers by marking 2 dot, 1 dot, 0 dot, and a negative 1 for good luck, to prove to the people that we know we're talking about the positive and negative whole numbers.